All right. So so that we saw that equation last time. Electric field equals the negative derivative of the voltage. And we also saw this similar to that equation is that your change in voltage equals the negative integral of E dot dr. Okay, so both of those equations are the same equation, just rewritten slightly. We could find the electric field if we know the voltage, right? If we know the potential, and all we got to do is take the derivative with respect to space, in this case r. Or if we have the electric field and we integrate the electric field along a certain path, that will give us a change in voltage. And also remember, I'm not sure if I stressed this last time, but I want to stress it now, that when we're looking at voltage, this is a scalar function. Okay, it's a scalar. Okay, so when we talk about voltage, we're not concerned about direction, about whether we need to take cosines or sines or just components in general. We don't have to do that because it's just a scalar. There's just numbers. Okay. Of course, electric field, like we know, are as a vector. Okay. So let me go back up to this top equation here for electric field. Where does the direction come from, right? If we're taking the derivative of the negative derivative of a potential, where does direction come from? Well, the more appropriate way of writing this is a negative, and you're going to see this new operator called a del operator. Maybe you guys have seen it before. You might get that a little bit better. NV. Okay, so this del operator, in it has direction. So, for example, in the Cartesian coordinates, this would be d dx I hat plus d dy. Oh man, I don't know. I think I need to clean my screen. I think this is why it's acting this way. J hat plus d dz k hat. Okay, so in Cartesian coordinates, that del operator, even though you're taking the derivative, has the unit vectors in it. Okay, so and of course there's a different function in different coordinate systems. So yeah, spherical coordinates has their own del operator. Cylindrical coordinates have their own del operator. Now you guys don't have to worry about that in our class. But I do want to stress the whole reason why I'm doing that is to stress that right here, you know, these unit vectors does give us a vector overall when we take the derivative here. Okay, so we will go from a scalar, use the del operator, and gives us a vector. Okay, so that's where that vector nature comes from. Over here, you take the dot product, right? Remember, another word for dot product is also known as a scalar product. So this scalar, or this dot product, gives you a scalar right after you do the integral, and so that gives you back your scalar here. Okay, so really important equations as far as going from potential to electric field, and we talked about some key concepts there, key ideas with the electric field and potential. Let me see. I think I have them here on my slides. Let's see. I guess you guys could look back, but we're saying that the electric field, I can't find them on the slides right now. The electric field is always perpendicular to your equipotential lines. We also said that electric field always goes in the direction of decreasing potential, and we said one more thing that pretty much what this equation tells us, that how quickly the voltage changes or the potential changes tells us how strong our electric field. So stronger change in voltage or quicker change in voltage over distance means a high electric field. All right, so Karen, are both V's next to the, are those both V's next to the dVdr? Right here? No, this is not a V. This is a del operator. So I could write that a little bit clearer. I'll try my best. It's kind of an upside down triangle, right? As opposed to the V. And it's a little vector. So yeah, that first one. Sorry, I just still didn't draw it neatly enough. Yeah, but it's an upside down triangle, and that upside down triangle is a symbol for the del operator. Okay. All right, so what I want to do today, so we talked about those relationships last time, those three characteristics that I just mentioned. We talked about those last class. What I want to do today is apply these to a couple of problems of how do we actually use this in a problem. So we're going to do just, I think I only have 2 examples in mind here that we're going to be looking at. And we jump into capacitors today after that. Okay, so let me get here. So we just want to find the potential of a solid sphere of charge. Okay, so we have if you want to see a quick picture of this. Okay, so we have a sphere, and that sphere is filled up with charge. And we'll just say it's uniform charge density. Okay, it'll probably be better if we just do this. Okay, uniform charge density there. And what we want to do is find the potential anywhere inside this this sphere, on the inside of the sphere and on the outside of the sphere. Okay, so one thing we know about this, and I'm not going to reprove it because this is we can use Gauss's law. Gauss's law tells us electric field of this in this situation. So, so I'm not going to prove that again. So electric field on the outside we saw is KQ over R squared, where Q is a total distance. Q is a total charge of the sphere, Q, and R is your distance from the center. Okay, now if you remember from Gauss's law, when we looked on the inside of that, we got a different equation. Gauss's law gives us on the electric field on the inside, KQ R over R cubed. Okay, where that capital R is the radius of the sphere. I'm gonna try something. I'm gonna see if I could write neater. Make this more like a piece of paper for me. Hey, I think so. Okay. So the only thing is I can't type. All right. Okay, so we have E out KQ over R squared, E in KQ over R cubed. So what I want to do is find the voltage. What is the voltage at some points? And so voltage is always a difference. So when it says potential, one thing we have to remember is that potential is always a difference. So put potential is a difference in voltage. Okay, It's a difference in voltage. So you have to start somewhere. You have to have a zero. Where is that zero voltage being measured? Okay, so if you remember from a point charge, which is kind of like what we're looking at, right? The solid sphere, after you leave, after once you go outside of it, it acts like a point charge. So for any point charge, we say the voltage equals zero when R goes to infinity. Okay, and that's going to be my zero. So all my measurements are relative to that zero. Does that make sense? You know, if I'm trying to find the voltage at whatever point I'm looking at some point here, I don't know. Let's say I'm looking at the voltage here, point P, which is inside, you know, inside the radius, inside the sphere there. All my whatever voltage that is always going to be measured with reference to your zero voltage. In this case, zero voltage being infinity. Okay, so we're going to need that to know that. So let's go to how do we find voltage? We're going to use the electric field. Remember the equation I had. Let me put that different color. Remember the equation I had earlier. Delta V equals negative integral e dr. Okay, and we're going to see what is our, so we're talking about delta V, right? Your change in voltage. Well, that change in voltage is the difference between your initial and final positions here. Okay. That's what voltage always gives you. That equation is always giving you a difference between point A and point B. Now, what would be our initial position? Well, go look at the bottom left corner, right? I said my voltage is zero at infinity. So my initial position, I'm gonna put at the zero here. I'll put that in a different color. At the zero. So what position do I have zero voltage? Well, I get zero voltage at an initial position of infinity. Okay, so that way, all my voltages are measured from that zero value, right? My delta V, my change in voltage, my initial voltage would be zero if my initial position is at infinity. Hope that makes sense to you guys. Let me know if it doesn't. Okay, so sure. So let me explain that. So let me go to the next line, and maybe you'll see why. So the delta V, right? The delta V that I'm looking at here is always going to be my V final minus V initial, and that equals that, you know, that integral that I wrote here. Okay, so what is V initial then? Well, V initial is going to be wherever your initial whatever your initial position is. We don't know anything about voltage in this problem, right? If you look at the problem there, I didn't give you a number for voltage anywhere. The only thing you know about this problem is that voltage is zero at infinity. Okay, voltage is zero at infinity. So if I'm trying to find VF, right, voltage at some distance, point P there, then I need to know what VI is. Otherwise, I have two unknowns. If I set RI to be infinity, then I know what VI is. Right? If my R initial is infinity, that automatically makes V initial, my initial voltage, to be zero. Okay, so that's why I'm doing that. All right, that makes sense. So so now I know my limits here. Right, my limit, if R initial is infinity, our final, right, this position is going to be wherever position P is at. Okay, so if we look at my picture here, P is at some position. I haven't defined that position yet, so let me just give that a let's see. And call this lowercase r. Okay, so I'll just call that my position for P. All right, so what I have now Let me erase this really quick so I could keep writing here. So my integral, so I have negative integral from infinity to r, right? Where r is at point P. It's inside the sphere. E dot dr. All right. Okay. So there's a problem with this. Oh, so I could simplify it in the next line here. V final. If r is infinity, right? My initial r is infinity. I just said vi. V initial is just going to be 0. That's how we defined V initial. So the left side just becomes V final. All right, is my voltage at point P. Oops. I'm going to have a problem with this E. So that E, as you can see in the black there, that E changes functions. Right? On the E out, you have a certain equation, KQ over R squared. Once you go inside the what's called the sphere, that electric field changes. Okay, so maybe I could draw this really quick. I'm gonna have to erase some of this E stuff here. I'll rewrite it in a second. But we need to think about it this way. We're looking at a point at a difference in voltage between here, when R equals infinity, and we're going this way to here. Right, that's kind of my path. It goes from infinity, where we know our voltage equals 0 here, and we're going to VP, and we don't know the voltage at P. That's what we're trying to find. Okay, but we do know how electric field changes. On the outside, it's KQ over R squared, but on the inside, our electric field is what I wrote earlier, the KQ R over R cubed. Okay, so we have that change in function. How do we deal with that change in function in my integral? We got to separate the integral. I'm going from infinity to R, and that'll be E out, dr, plus the integral from R to lowercase r, and that'll be the function E in, dr. All right. Oh, I forgot my dot products. Okay. All right. So let's see here. So E and the electric field and the R direction are in the same direction. So that dot product would just go away. If you take the dot product of two vectors that are parallel, you get well, you get 1, right? Or you get cosine of 0. So that dot product would just go away because E vector and the R vector are both outwards, right? We know electric field from a positive charge goes outwards. So E and R in the same direction. So I'm going to plug in my equations here. E out, KQ over R squared dr, minus integral R to lowercase r, and E in, KQ R over R cubed. Let's do that one again. dr. Okay, so let me know how you guys are doing with this. I know this could get a little intimidating because, you know, once we start throwing in integrals and remembering that we have to think about how the function changes, you know, I could lose some of you. So just let me know if you want me to review any of these steps again. But I think once we get this, we're pretty much in autopilot now because it's just doing the integral. Okay, so let's do the integral here. KQ, we'll do the first one. We're gonna watch out for those limits though. Actually, let me go to the next page here because I'm gonna run out of space. So voltage at point P, you get negative integral. Well, that integral would just be KQ integral of infinity to R, capital R, of, let's see, what was inside? dr over r squared, okay? And then the other one, the constants I could take out from the other ones, KQ r cubed, integral from capital R to lowercase r, and on the inside of the integral, I think it's just r dr. Let me know if I make a mistake there, but I'm pretty sure that's what I would get just just taking out my constants. So negative KQ, that integral, which just becomes, what was that? I get a negative there, don't I? Negative 1 over r cubed. And I'm going to plug in my limits, infinity to r. Same thing here. I have my constants. And this one gives me an r squared over 2 with my limits, capital R to lowercase r. All right. Let's see here. Now it's as simple as plugging in my limits. So the negative on the, I'm looking at the first term here. This negative right here and this negative will cancel out. And then infinity, you know, once you plug in infinity in your denominator, that just goes to 0. So that infinity is not going to show up in our equation. I just really need to plug in capital R here. So I would get, if I do that, KQ over capital R cubed minus, and then on the other term, I still have my constant out here. And we're going to multiply that by, let me plug in my limits. One second. Oh yeah, that's my mistake. I knew I made a mistake somewhere. All right, I'll go back to that, Jake. 1 second. R squared over 2 minus capital R squared over 2. All right, so yeah, my mistake earlier. Really simple mistake. Integral of r to the negative 2 is not, you don't get an r cubed there. All right, we get just r. So this would just be r. What was I thinking? I guess I just did the derivative, right? Instead of taking the integral. All right, so there's our equation. We could, can we even simplify that? I don't know if we can or not. We'll probably factor out the KQ over R. Where does 3 come from? Oh, it's cubed. Let's see here. Where's my erase? So let me put cubed here. I'm trying to see if I could, oh yeah, I could definitely factor this out. It's kind of a weird function though, but this is what I get. If I factor everything out, factor out the KQ over R, and I would get a 2 there. because of that 2 in the denominator, the r squared over 2. And you get b minus r squared over, I think this will be r cubed. No, it should be r squared. Where did r squared come from? Oh, no, yeah, r squared. Doing too much math in my head. Maybe you guys should double check my algebra there. But I kind of just want to move on. That's what I'm doing in my head. Okay, so this is our voltage here. Voltage at point P, right, which is inside the integral, or inside the, not inside the integral, inside the sphere of charge. Okay, so we used the whole point here. We used our electric field from earlier, the electric field from a sphere of charge, and we, from that electric field, we used it to find voltage. Okay, so there is you can kind of see the subtleties there. Where we're finding voltage is always a difference in voltage, so you have to set your zero, or you have to have a known value somewhere. That's why back here we chose our initial position to be at infinity, because that gave me my 0 voltage. Okay, and I was able to then get rid of this V initial. All right, so my problem only had one unknown, which is the final voltage. Okay, so that tells me the voltage at P is that if that voltage was outside the integral, I keep saying that. If that point P was outside the sphere, then we wouldn't need this whole term. This whole term will drop off. The only reason why we had this term in the first place was because we needed the electric field when you get inside the sphere. If point P was just outside, we would just have to do this integral. So it would definitely become a lot easier if we were on the outside. But because that point P was inside, we had to use this one and the electric field on the inside.